Okay, yeah, I'm Tim. I'm an owner-builder building in the Adelaide Hills in Aldgate. And I want to pose a question. Looking at heavy earth, we get looking at trying to work out the R values of our bricks, but I would like to suggest that R value is actually not a valid measurement. Now, I'm not going to say is it relevant. I'm going to say I don't think it's actually a valid measurement when we're looking at a heavy earth. Part of the definition for measuring R value is reaching a steady state. In a heavy earth wall, we don't reach the steady state. And so I think we need an entirely different paradigm for measuring the performance of a heavy earth wall, because the R value is just not the measurement that is appropriate to that context. So what I've done in trying to work out how I need to build my walls is I've embedded some temperature measuring sensors right through the wall. And I'm using a little electronic sensor. They come in a sealed metal container, so I can bury that in the wall, and it's pretty tough and it survives there. And in the quantity, these are about $2 a piece, so they're, disposable thing. The logging doesn't need to be expensive. I'm using a handful of these and a little Arduino microcontroller that you can buy on eBay for $10 or less. So that's working well. Now, I've had this logging some data for a while now. And so I've got one file here that's got a few data intervals. I've got about 43,000 data points in here. This is 18 months worth of data. Now, there's a few bits that I don't need to be looking at, so I'll make it simpler. But what I want to look at is what's happening on a day-to-day basis. So I've got here the temperature at the surface of the wall, and in the midsummer heat wave, we've got the 40-degree air or surface temperature there. But if we look at the temperature in the core of the wall, once the wall is starting to heat up in the morning, the core of the wall is still dropping. So the whole concept behind the R value, I think, is flawed, that you don't have this steady state flow. You have this sort of shift, as it's been said several times, a thermal lag. The heat is flowing through the wall. Now, this is data from, as yet, just a freestanding wall, so it's outside air on both sides.
Tim, could you explain that graph on the one of each of the P?
Right. This is, I've got 14 days worth across here. So this is, these smooth lines here are the temperatures deep in the core of the wall. The highest temperature I've got here is 25 and a bit degrees, when the outside temperature is 41 degrees. So this is looking at the difference between the temperature at the surface of the wall and the temperature deep in the core of the wall. This is rammed earth, essentially 700 millimetres thick. So this is to create a big thermal mass, which is giving me that thermal lag. Excuse me.
Rammed tyres?
Yes. But it's essentially solid earth.
Aspect is what, north or?
This is a wall that is running north-south, so it is east and west surfaces. As I said, At the point that I logged this data, it's a freestanding wall. So I'm just wanting to make the point that we've got an entirely different system happening than what the modelling or than what the regulations is. The best modelling is starting to get a handle on what is actually happening here. But we've actually got a different situation in reality. So this, in a heat wave, I've got 40 degree surface temperatures, but the assumption of the R value that the heat is reaching the other side of the wall doesn't occur. The
9-degree nighttime temperatures there.
Yeah, that could be with perhaps a bit of humidity evaporating from the wall. Something that will be not an air temperature, but this is a sensor embedded right in the surface of the wall. So if it got a bit damp, it would have gotten down to that, yes. So this is, I've got a surface temperature and then a little way in and then the deep core of the wall there. So, yeah, I'm just wanting to say that this is an example of what we've been talking about with the thermal lag and so forth, and that I think the concept of using an R value to assess a heavy wall is the wrong way to be looking at it. We don't reach the conditions under which R value is measured. And that looking at a heavy thermal wall as a passive device, I think, is the wrong idea. It's not functioning as a passive device. Once you've got a high ambient temperature, this isn't merely slowly transmitting that heat. It is absorbing that heat. It is taking the heat out. It's not functioning as a passive system. So your free-running house, if you're looking at a high thermal mass, it's not a passive system. It is an active system. It's just a passive active system, if you like, that it's not having an energy input, but it is actively moderating the energy. It's not merely passively transmitting the energy there.
Which line is the east side and which is the west side?
I'm going to guess that this blue line is the east side and this is the west side. I don't actually have that data in front of me right at the moment. It's just saying that this is having the first rise, so I'm assuming that's getting the earliest heat, and the later higher heat is the west side.
Do you have any data points like 15 or 20% humidity?
That will be like this green line here, which is sort of getting there, but not as extreme.
Did you stabilize that render floor?
Yes, with rubber around it. No, it's just dirt pounded in. It's no cement.
When you think about the effectiveness as a lag with mixed in cement, do you have any feel?
I have no idea. No. I have a few, I guess, philosophical goals for my construction. One is that there will be absolutely no MDF in the building and as little cement as possible. I will use some because, there are points where you can't beat it, but
Maybe a cement stabilised round earth wall manufacturer can finance you to do that.
if they want to, I can do that, yes. But I don't need cement for the bulk of what I'm doing. So
Does the rubber, does the heat actually go through the, like, hits the rubber or hits the earth? Is the rubber an actual barrier on the outside that it goes through?
I guess that is a small component, but you've got maybe a centimetre of rubber compared to 68 centimetres of earth. So and the rubber isn't continuous. So I guess I could, conceivably do a comparison of just inside and just outside the rubber at some point, but I haven't done anything like that.
Where have we got the sensors compared to the actual tyre?
Oh, halfway up, rough. Yeah. But then they're actually in a gap between the tyres really more than I have, on that. So, hang on, I've got to go back.
The distance between the peak of the centre and the peak of external.
12 hours peak to trough.
So there's a day, 1 day, so I guess that might not be the best one to... I've got one probe is just under the surface. One probe is a quarter of the way through, so that's about, 180 millimetres. One probe in the very middle, 3/4 and just under the other surface.
So that green line is effectively the same.
Yes. But yep, sure. So I guess I'm looking at the lag here. Here's the lowest point of the core temperature. 6 hours. Well, here's your peak daytime temperature. Maybe that's 4 hours from the peak surface to the peak core temperature. And that's in a freestanding wall. So this has got no roof on it at this point of data logging. I had intended to get some more recent data, but I forgot as I was driving off to go and collect it. So we can see through the year, if I have a look at some winter temperatures, I think I decided...
Interval of measurement, is it hours or minutes? Or?
I'm logging at 15 minutes in this. It helps me get the sense of the flow through it. My setup can log whatever interval you care for. So even in midwinter, I've got some 1 degree temperatures here. The wall is still, and this is, as I said, a completely freestanding exposed wall. It's sort of 7 to 15 degrees with no protection.
Is this just one set of sensors, or did you sensors in different places and average them?
This is the data from one set of sensors, but what I'm actually doing is I have a U of walls. I'm building one wall that has berm and insulation. I'll have another wall which is bermed, but there is no insulation, and a third wall which is freestanding. So next year's conference, I'll have all three sets of data to show you.
All oriented the same way.
Sorry?
They should be all oriented the same way.
I don't have the resources to build walls for no purpose other than testing. This is putting the testing into the structure that I'm building.
Well, in the 1 meter length, 2 meters length of the wall of insulation, the other one with glass,
It would be challenging to sufficiently isolate those. I've got 8 metres between the sets of sensors.
But you won't be able to compare the data. You have different orientation.
It will actually, it won't matter for what I'm building. They're bermed and then roofed, so there won't be sunlight hitting the walls. It will be ambient air to wall to berm, ambient air to wall to insulation to berm. So it,
What I'm a bit shocked is that in 600 thick under wall, you only have a fan like for 4 hours.
well, I guess this is,
That's a bad news.
being a freestanding wall, you've got the ambient air is only 300 millimetres from the core, not 600. So I would have morning sun hitting one side of it still at this point.
Can you talk about the position of the sensors? Because if you have it in the tile wall, how is it in relation to the rubber? Because rubber conduces quite well.
I've actually positioned these outside of the tyre structure. It's in the fill in between them. I probably should stick one inside the tyre just to see how that looks, but I would be assuming that the very deep core is not going to vary much along the length of the wall. Whether,
I think where the gap is between the tires, the temperature, you travel faster inside the tire.
possibly.
The steel in the steel reinforced inside the tyre, you're transmitting heat because it's steel, even though it's encapsulated in the rubber.
Yeah.
To some degree, maybe negligible, but it might be providing a sort of highway or slow way to
Possibly.
get called.
That might be the explanation of why the quarterway temperature is so much closer to the surface than it is to the core.
Good question.
Yeah. So if that's it, I'm done.